Right. In the last video, we looked at the Henderson-Hasselbalch equation, where we used ethanoic acid and its conjugate base to derive the Henderson-Hasselbalch equation, which is given by pH equals to pKa plus log of B divided by A, where B is the base and A is the acid. Now, let's go ahead and look at this question here and see if we can use this equation to work out the pH. Here we go. What is the pH of a solution consisting of a 0.75 molar ethanoic acid and 0.5 molar sodium ethanoate? The Ka of the acid is 1.8 times 10 to the power 5. So here we've got a buffer solution consisting of the salt here, or the base, and a weak acid. So this is an acidic buffer. We got a weak acid and its conjugate base, sodium ethanoate. So let's look at what we know. What do we know? We know B, which is the base, to be 0.5 mole. We also know the acid A to be 0.75 mole. Now, what don't we know? We do not know pKa in the question. So we can go ahead and first of all find pKa and plug that into the equation to work out the pH. Now, how can we work out pKa? We know that pKa equals to negative log of Ka. Now, we've been given Ka as what? 1.8 times 10 to the power minus 5. So we can go ahead and plug this in. This implies that pKa equals to log of 1.8 times 10 to the power minus 5. Alright? Let me wipe this off. So we've got our pKa equals negative log of what? 1.8 times 10 to the power 5. Now, if we plug that in, we will have the pKa to be 4.7447. That is our pKa. So let's go ahead and then put in the values here. Our pH then will be 4.7 here plus log of our base, which is 0.5 here, divided by our acid, which is 0.75. Alright, now put that in your calculator, and what do you get? You're going to have, let me put the moles here, they will cancel out anyway. So if you do this, you're going to have our pH will be 4.7447 plus log of 0.667. Okay, Therefore, our pH will be equals to 4.7447 minus 0.176. Okay, now our pH would therefore will work out to be 4.57. So that's how you can use the Anderson-Hasselbalch equation to work out the pH. Now let's look at another type of question. Here we've got we are required to determine the pH of a buffer containing 0.1 mole of ammonium chloride and 1.5 mole of ammonia, and the Kb of the ammonia is given as 1.8 times, again 10 raised to the power 5. Okay, so here we've been given the Kb. Remember that this buffer consists of ammonium chloride and ammonia, a weak base and its conjugate acid. A weak base and its conjugate acid. Now, so here, what do we know here? We know the Kb, which is given to us as 1.8 times 10 raised to the power minus 5. We also know the number of moles of ammonium chloride. Okay, that is given to us as 0.15 mole, and our weak base, which is 1.5 mole. Okay, now we've been given Kb. Remember our equation is pH equals to pKa plus log of base over acid. Okay, now we have pKa in our equation. We do not have pKa in the question. We have to use the Kb to find the pKb and use the pKb to find our Ka, so that we can plug that into our equation, our pKa. Okay, so first of all, let's find pKb. pKb equals to negative log of Kb. If you remember our previous lesson, we knew that pKb equals to negative log of Kb, just as pKa equals to negative log of Ka. So we have our Kb, we can work out the pKb. So let's go ahead and put the figures in. Our pKb will be negative log of our Kb, which is 1.8 times 10 raised to the power minus 5. All right, great. Now when we do that, our pKb will be 4. Let's plug them in. Our pKb will be 4.744. We knew this from the previous question 7. All right, that's our pKb. Now we know that pKb plus pKa equals to 14. Therefore, we can rearrange the equation and make pKa the subject in which case we're going to have pKa equals to 14 minus our pKb, which we've just worked. Let's plug the figures in. pH, pKa equals to 14 minus 4.777. Yeah, that comes to pKa to be 9.255. Okay, that will be our pKa. So now we know our pKa. We can go back into our original equation and plug the figures in. Okay, our pH would therefore be the pKa, which is 9.25527 plus log of our base, which is 1.5. Okay, 1.5 divided by 0.15, and that's going to give us a pH of 10.255. Okay, so here we were given the Kb without the pKa. What we need to do is to use the Kb to find the pKb and subtract pKb from 14 in order to get the Ka, and plug them in and work out your pH. So that's how this one worked too. Let's look at another type of buffer solution calculation, where here you are given the mass of the various components and you are supposed to work out the pH. Now here we have calculate the pH of a solution containing 20 grams of acetic acid and 41 grams of sodium ethanoate in 850 ml of solution. We have been given the Ka again of the acid. Okay, so what we want to do is to plug them in. We have the masses. So in order to work out the number of moles for the calculation, we need to work out the molar masses of the various component, the acid and the salt. Okay, so here we've been given the masses. What is the number of moles of ethanoic acid? Now, number of moles of CH3COO will be equals to the mass divided by the reacting molar mass. Now, what is the MR of acetic acid? What is the MR of acetic acid? That is 60.05. Okay, and therefore number of moles of our acetic acid will be equals to the mass, which was given to us as 20 gram, divided by 60.05, which is equals to 0.33 mole. Now let's go ahead and work out the number of moles of the other component, which is the salt or the base. That will be MR of will be equals to the mass again, which is 41 divided by the relative molar mass of sodium, which is 83.03, and that should give us 0.49 mole. Okay, so now we know the moles of the base and the salt. We also know the Ka, so we can then go ahead and work out the pKa. Our Ka equals to 7.2 times 10 raised to the power. Let me grab the eraser. Okay, 7.2 times 10 raised to the power. Let me see, 1, 2, 3, 4, 5 minus 5. Okay, therefore our pKa will be equals to negative log of 7.2 times 10 raised to the power minus 5. Okay, that will be 3.1427. Now we know our pKa. We can go ahead and plug the figures in the equation and work out our pH. pH will therefore be the pKa, which is 3.1427 plus the log of the base divided by the acid. Okay, so we got our base, which is 0.49 divided by our acid 0.33, and that should give us a pH of 3.314. Okay, our pH will be 3.314. So that's how you can use the Henderson-Hasselbalch equation to determine the pH of various